Hello everybody. So in this video, we're going to look at the step response in RC circuits, right? So far, when we have looked at this particular circuit, we have used this circuit to charge a capacitor or a equivalent circuit to, to ramp up an inductor with current, right? So, and so far we have said, okay, assume that this switch over here, we assume that the switch is closed for a long time, and then after a long time when the circuit reaches steady state, the all voltages will be DC voltages, and since the voltage here would be DC, there will not be any current going through the circuit, and the voltage across the capacitor will be equal to V, right? So that's what we saw so far when we were looking at like the steady state. So now what we want to consider is how does this circuit exactly reach that steady state, like what would be the mathematical expression to reach the steady state, right? So what we're going to do now is close this switch at t equal to 0, right? Instead of minus infinity, we're going to close that at t equal to 0 and see how the circuit actually responds to that action, right? Now if you notice, for this part of the circuit, if you look at the input to that circuit, since the switch is closed for negative times, the input looks as if it's 0 for negative t, and starting at t equal to 0, it becomes V, right? So this particular input function looks like a step, right? So that's why it's called a step response, right? So what we're saying is, how does the circuit respond if your input looks like a step function? So that's what we're going to look at right now. Okay, so let's start writing some KVL equations here. So if you look at that circuit, I can say the voltage across the capacitor would be equal to my V minus R times I of t, right? For t greater than or equal to 0, obviously, right? So that's about circuits basically, right? So I used a KVL equation and I got this equation, and from here on it's all differential equations. So let's look into this. There's one small part from physics we need to pick. That would be, this would be, the right hand side will be equal to V minus R. I of t is C times the derivative of VC of t. Okay, so that's it. That's about circuits and physics, right? From here on it's all differential equations. So I'm going to rearrange this. So I have RC times the derivative of the voltage plus VC of t. This will be equal to V, right? So if you notice, this is a first order differential equation. And if you try to recall how you solve first order differential equations, right? Any differential equation, you have to do two things, right? First is find the natural response, or some in differential equations lingo it will be called characteristic equation. So first solve the characteristic equation, and then, or you can also sometimes you first find the characteristic solution, and then to find the forced solution, and then the actual result, the actual solution for this differential equation will be a linear combination of these two solutions, right? Okay, so if you want to find first the characteristic solution, what you do is you set the input to 0 and find and look and see what sort of solutions these partial differential equations satisfy when there is no input, right? So that means you're saying, okay, RC times the derivative of VC of t plus VC of t equal to 0. You solve this first, okay? And so the solution to this equation would be the characteristic solution, right? So again, so I can use my, when you're solving characteristic solution, I don't want to go into details of why we do what I'm going to do, but I'm just going to say, okay, say what we're going to do. So replace, if we have a derivative, you replace that with lambda. If you have a double derivative, replace that with lambda squared, and so on. So I'm going to say RC times lambda plus 1 equal to 0, right? And 1 would be the case when there is no derivative. And so the roots of this equation are, and this is called the characteristic equation of the partial differential equation, characteristic equation. Okay, so this means lambda is equal to -1 over RC. Okay, so then that if this is the root, then the characteristic solution would be Vc of t would be equal to e to the minus t over rc. Okay, and I know I'm just telling you, okay, this is how you do it. There's a reason why we do each of these steps, and I'm assuming you covered that in your differential equations class, right? Uh, and if you don't know why we do exactly these things, I very strongly recommend for you guys to go back into your differential equations lecture notes or homeworks or material and look at why we do exactly this. Right? Each of this has a reason. We're not just not okay, step one, do this, step two, do this. There's a reason why we do this, and this is called the characteristics solution. Okay, but again, all that is out of scope for this course. I won't go into the details. So second is a forced solution. So let me write down the equation again. So we have RC times the derivative of Vc of t plus Vc of t is equal to V. So the first thing I want to do is take the Laplace transform on both sides. Okay, so I have RC times S plus 1 of Laplace transform of Vc. This will be equal to V over S on the right hand side. Okay, so this means my Vc of S would be equal to V over S times 1 over 1 plus RC times S. Okay, and then I can write the right hand side as a sum of two fractions. Okay, so that will be V times 1 over S minus RC times 1 plus RC of S. Okay, again, if you recall your partial differential equations course, I think you did you did this fractions separation of a fraction into sum of fractions, right? So you want to go and look into that. In this case, it's a bit it's slightly easy on how to write this as a sum of fractions, but in general there is a more there's a procedure you can follow to get this. Right. So now the reason I did this is now it's easy for me to calculate the inverse Laplace transform. So first I want to get this into a familiar form, 1 over S minus 1 over S plus 1 over RC. Okay, so this is 1 over S, and this right hand side, this is 1 over S. This is 1 over in the form of 1 over S plus A, which I can find the inverse Laplace transform. So this means my Vc of t would be equal to the inverse Laplace transform on the right hand side would be 1 minus e to the minus t over RC. And this is my forced solution. So the total solution would be a linear combination of these two, right? So total solution would be a linear combination of these two. So Vc of t should be equal to C1 times the characteristic solution, which is e to the minus t over RC, plus C2 times the forced solution, which is V times 1 minus e to the minus t over RC. Now the next thing for me to do is find out what the C1 and C2 are. So we know, if you look at the circuit all the way at the top, okay, so before the switch is open, the voltage across the before the switch is closed at time t equal to 0, that means for negative times, the voltage across the capacitor is 0 because there is no charge on it. Okay. Now, as soon as the switch is closed, the voltage across the capacitor continues to be 0, right? Because the voltage across the capacitor cannot change instantaneously, right? So because we have I of t is C times the derivative of Vc of t. If the voltage changes instantaneously, that means it requires infinite amount of current, which is not possible in general. So which is not possible. So the voltage across the capacitor remains continuous. That means at t equal to 0, the voltage here would be 0, right? And then we also talked about, okay, what happens when t equal to infinity? That means we have waited for a long time, everything is steady state, and the current through this circuit will be 0, and the voltage across Vc will be equal to V. Right, so now we know two values, right? What is Vc of t when t is 0, and what is Vc of t when t equal to infinity? We're going to use that to figure out what our constants are. So first I'm going to say Vc of 0 is equal to 0, and then substitute the t equal to 0 on right hand side. That will be c1 plus c2 times v times 1 minus e to the 0, right? So this right hand side will be equal to c1. So this implies c1 is equal to 0. And then I know vc of infinity is equal to v, right? And then I'm going to put that on the right hand side. I know c1 is 0 now, so I'm just going to say c2 times capital V times 1 minus e to the infinity into the minus infinity, right? So this is equal to c2 times v. So this implies my c2 is equal to 1, right? So now I have c1 is equal to 0 and c2 equal to 1. Therefore, the total solution for my voltage Vc of t is equal to capital V times 1 minus e to the minus t over RC. Okay, so now let's see if our initial and final conditions satisfy, right? So if I say Vc of 0 will be equal to V times 1 minus e to the minus 0, e to the minus 0 is 1, so this will be equal to 0, which is, which satisfies with what we know about the capacitor. And then if you do Vc of infinity, that will be equal to V times 1 minus e to the minus infinity, which will be equal to V, right? Which also we know, right? So if you plot this as a curve, this will be Vc of t, and this is time, let's say, and this value is V, and then this particular curve 1 minus e to the minus t over RC will look, we use a different color here, it will look something like that. Okay, so it will never quite reach V, but it will get closer and closer and being very fast. And it will start at 0, and that's how it reaches, right? So far we've been talking, okay, at steady state the voltage will be V, right? So this equation tells you how it will get there, right? Okay, now you can do a similar derivation for RL circuits. Let's consider a circuit where you have a current source, a DC current source, a resistor in parallel R, and then an inductor. Okay, and let's say there was a switch here like that, and then the switch is closed at t equal to 0. So we know, when at t equal to infinity, everything should be DC currents, right? So if there's a DC current through the inductor L, then the voltage drop across it should be 0. The voltage drop VL should be equal to 0 at t equal to infinity, right? So that means there will not be any current going through here, and all the current will go through the inductor. So let's see. So if this is IL of t, then I know two facts about IL of t. IL of 0 will be equal to 0 because the switch is open for negative times, and the current through inductor is continuous. And then I know IL of infinity is equal to I at steady state, right? But the real question is how does the current in the inductor go from 0 to I, right? What is the mathematical expression? And I mean, if you have to guess, I think you will guess IL of t would be equal to I times 1 minus e to the minus t over L over R, because L over R is the time constant for this circuit. Okay, so again, the derivation will be very similar to the derivation we made above for the RC circuit, but I very strongly recommend for you guys to go through a derivation yourself, right? It will be a good refresher for your differential equations material you learned in your prerequisites. Okay.